In this video, we're going to take a look at related rates in calculus. In particular, we're going to take a look at the cone problem two different ways, and we're also going to see another application involving a triangle. First thing I'd like you to notice is whenever we're working with related rate problems, we're basically going to need what I call an in equation. In the case of the cone, it will typically be the volume of the cone. And we'll typically take the derivative with respect to time, we'll ddt it, and as a result here, you're going to notice we have the chain rule involved, as well as the product rule, because volume is a function of radius and height. But another option is going to be if there's a relationship between radius and height, to put volume in terms of radius or volumes in terms of height, and then we'll have an easier problem that doesn't involve the product rule. Let's jump in and take a look at our examples. So example one, we have the volume of a cone. You're given the equation for volume, increasing at a rate of 28 pi cubic units per second. So right away, I just like to write down what I'm given. So that means dV dt is equal to 28 pi. And I'm not going to worry about units here. You're not trying to be tricked anywhere. But what is important is whether something's increasing or decreasing in terms of positive or negative. And again, we're increasing, so it's positive. At the instant when the radius of the cone is 3, so this is at r equals 3, we know that the volume is 12 pi cubic units, and the radius is increasing at a rate of 1/2 unit per second. So that's dr dt is equal to 1/2. So notice this is very important. This is at a particular instant. We're not told how radius and height are connected. We're not told anything else about this. So we can't assume that it's a fixed cone. So now let's look at our question. At the instant when the radius is 3, so that's under these conditions, what is the rate of change of the area of its base? So as you recall, here is a cone with the base at the bottom here, and the base is a circle. So the area of the base, we can use A or uppercase B, is equal to pi r squared. That's our inequation. So what we're going to do now is just ddt this. And if we ddt, we're basically using implicit or the chain rule. The letters don't match, so the derivative of A with respect to t is simply dA dt. And when we ddt pi r squared, we just look at the radius and we just use the power rule, and we have 2 pi r, but again, r is a function of t, so we're going to have to multiply by dr dt. Once we have this, we can enter our information for when the radius is equal to 3. So that means dA dt will be equal to 2 pi. Our radius is 3 at that instant, and dr dt is 1/2. And simplifying that, we simply get 3 pi, and that would be cubic units, so we'll label it cubic units per second. And that is our answer for dA dt. Second part, at the instant when the radius is 3 units, so again, we're at that time, what is the rate of change of its height, h? So now we need something that involves h, and the only thing we can use now is the formula for volume. So I'll write that as pi over 3 r squared h. This is where we ddt this, and naturally we're going to get dv dt on the left side. And now pi over 3 is a constant, so I just like to leave that on the outside and just focus on r squared times h, which notice is the product rule. So we take the derivative of the first, 2r, but again, it's going to be times dr dt, because we're taking the derivative with respect to t, times h, plus the derivative of h is simply dh dt times r squared. And this is where we just substitute in the values we were given. So we were given dV dt is 28 pi. We have pi over 3. 2 times our radius at that time is 3. dr dt is 1/2. Oh, we're stuck. Suddenly we're stuck because we don't know the value of h at this time. So we're going to have to find some way to determine this. So what we can do is we can go ahead and we're going to write down that we know the volume is equal to pi over 3 r squared h. And we're looking at the instant when the radius is 3. So we're going to have 3 squared times h, and we have pi over 3. And at that time, if you remember, they told us that the volume is 12 pi cubic units. So I can go back here and say, all right, volume is 12 pi. And solving for that, we can cancel the pi's. We have 3 squared divided by 3, so we have 12 equals 3h. So that means at this time, h is equals 4 when the radius is 3. So all for the same instant. So now we can go ahead and put 4 plus dh dt times our radius squared. So we'll just go ahead and write 3 squared. Now we just have to solve for this. So again, some nice things happen. We can notice the pi's cancel. I can multiply 3 to the other side. So I'm going to have 84 equals, and we multiply all this out. 2 times a half is 1. We end up with 12 plus 9 dh dt. And if we subtract 12 and divide by 9, we find out at this instant, dh dt at r equals 3 is simply equal to 8, and that's units per second if we want to write that down. Okay, on to part 3. At the instant when the radius of cone is 3, so again, all under the same conditions here, what is the instantaneous rate of change of the area, so dA, with respect to its height? So it throws a little curveball here, because they're looking for dA dH, and we need some way to relate these two. But you'll recall that we already found out what dA dt was and dH dt was. So via the chain rule, we know that dA dH is equivalent to dA dt over dH dt. So this is simply going to be 3 pi over 8. And the units will work out nice, so that will still be cubic units per unit. All right, so on to a different type of cone problem. So in this one, they're talking about a conical water tank with the vertex down and has a radius of 10 at the top and it's 24 feet high. So we know the fixed cone, the radius is 10 and the height is 24. Water flows in, so again, that means we have dV dt at a rate of 20 cubic feet per minute. Again, I'm not going to write the units down, we'll just write 20. How fast is the depth of the water increasing? So that means we're looking for dH dt when the water is 16 feet. So evaluated at h equals 16, and that's what we need. So again, we can simply start off with the equation of volume. So pi over 3 r squared h. So the problem here is we could go ahead and do what we did in that last problem and ddt it and use the product rule. But again, we're just concerned with h being 16, and we need a relationship between r and h. And at any time t rather, we know that there is a similar triangle here. And we know that for our new r and our new h, we can use the relationship that the radius of 10 over the height of 24, which we'll simplify to 5 over 12, will be equal to whatever the radius is over whatever the height is. So this is because of the similar triangles in there. And if we're going to do a cross section, we can just take a look at it like that. So now, since we're looking for dH dt, what we want to do is replace r. So that means r, we can say, is equal to 5/12 h. So we can rewrite this problem now and say that v is equal to pi over 3, and then r is going to be 5 over 12 h squared times h. We'll clean this up a little bit. All right, pi over 3, and I'll write this as 25 over 144. It'll be h squared times h, so that's h cubed. And I just like to leave the numbers there because sometimes good things happen. I can simplify at the end. And again, we're just going to ddt this. So this is our action. Now, we know that dv dt is going to be equal to, and we just have the power rule here, 3 times pi over 3. So I'll go ahead and write that down. We know those 3's are going to cancel. Times 25 over 144. And that's going to be h squared, but don't forget that dH dt. So often that gets left out. Because remember, because we are ddt'ing it, we have the chain rule involved because we're taking the derivative of h with respect to t. So we're assuming height is a function of time. So now we can go ahead and substitute in the values that we know. And we know that dv dt, we were given that was 20. And we canceled those two values out. So now we're left with pi times 25 over 144. And the height was 16, so 16 squared, or 16 times 16 if we want to write that, times dh dt. And we can clean this up a bit, whether or not we want to use calculators or not, doesn't really matter too much. So if we simplify this, this becomes 20 equals pi, 25, that 144, 16 goes to 144 9 times, so we can do that, just use 116 here, and then have dh dt. And from here, we could just divide that 16 over, have 20 divided by 16, multiply by 9 over 25, and that's going to equal dh dt times pi. So we're almost there. We'll simplify this a little bit more, and we know that we can have divide by 5 and we get 4, divide by 5, we get 5. Simplifying a little bit more, we have that 4 in the 16, so we have 1/4. So we're going to be left with 9 over 20 equals dh dt times pi, divide the pi over, and there we have dh dt equals 9 over 20 pi, and our units would be, if we go back up here, we're in feet, so that would be in feet per minute. And that's it for that one. All right, final problem we're going to take a look at is a classic triangle problem using a certain relationship. And let's just go ahead and read it. And we see that we have a ship traveling due west towards the lighthouse. All right, so that's ship A, it's going in. So that means the rate is decreasing, so that's negative. And that's at 15. So since that's x, we're going to call that dx dt is equal to negative 15. And we're not, again, I'm not going to worry about units here yet. And ship B is traveling away, north. So we're going to have dy dt equal to 10. Again, units are all fine there. So we have our given distances in terms of x and y, like they say, at time t, and y is that distance. So now here, part A, they're just kind of helping you out. Find the distance in kilometers between ship A and ship B. So they want you to find this missing distance, which we'll call z. So we see the relationship as a right triangle, so we can go ahead and use Pythagorean theorem to relate these three variables. Because again, all three of these are changing. None of them are fixed. If they were fixed, we'd replace it with a constant. So we should be able to see right away it's a 3, 4, 5 triangle. In case we don't, we can talk about substituting in the fact that this is 4 at an instant and this is 3 at an instant. So we'd have 16 plus 9 equals z squared, or z equals 5. And that would, again, be kilometers. So again, that was just kind of nice setup to show you the relationship between x, y, and z. So now they want the rate of change of the distance between the two ships. So that means they're looking for dz dt. So again, we can start with our equation, which is going to be x squared plus y squared equals z squared. And we're just going to go ahead and ddt that. And again, we're looking at the fact that x, y, and z are all functions of time. So we'll have 2x dx dt plus 2y dy dt equals 2z dz dt. And since we see 2 as a factor of everything, we can just go ahead and cancel that out. And we can substitute in the values we were given. Again, most important thing are the signs. So we have x, which at that time is 4, times dx dt, which is negative 15, plus y, which at that time is 3, dy dt is 10, and that is equal to z, and at that time z is equal to 5, times dz dt. And simplifying that, we get negative 60 plus 30 equal to 5 dz dt. So negative 30 equals 5 dz dt. So we have dz dt equal to negative 6. And again, that's going to be kilometers per hour. Final part of the problem involves theta. Sometimes people get scared, but this is kind of nice. So now we have this angle theta shown in the figure again. And again, remember, we have the same values going on in terms of y equaling 3 and x equaling 4 at that time, which they gave us there. And we have the same rates. So we need a relationship involving theta. And we have options. To me, the obvious one is going to be looking at tangent because we have opposite and adjacent. I would not involve the z just because that wasn't given information, but you can do that. That is okay. So we're going to start off with the tangent of theta equaling y over x. And again, they are all variables. So you know what we're going to do. We're going to ddt this. And in doing that, the derivative of tangent we should know is secant squared of theta. But again, we have to multiply by d theta dt. So as I like to say, the letters don't match, so we have that kick at the end, equals. Now we have the quotient rule because it's y over x. So if we d dt y, we're going to have dy dt times the bottom, which is x, minus derivative of the bottom, which is dx dt, times the top, which is y, all over the bottom squared. And simplifying this a little bit, we could just go ahead and write d theta dt is equal to, and we'll start to plug in. We knew dy dt at that time, if we just scooch up a bit just to make sure, dy dt was equal to 10. So we have 10 times our x value, which is 4, minus our dx dt, which was negative 15, times our y value, which was 3, all over the x value squared. So we're going to have 16 times, and when we divide by secant squared, that's going to be the same as multiplying by cosine squared of theta. Now, if you look at the picture, we have that y is equal to 3, and x is equal to 4, and z is equal to 5. So the cosine is 4 over 5 for the cosine of theta. So we know cosine theta equals 4 over 5. So we can replace cosine squared of theta with 4 over 5 squared, which is simply 16 over 25. And let's see if we can clean this up a little bit. So we will have 40 plus 45 over 16 times 16 over 25. That worked out nice. Those 16 cancels, and we're left with 85 over 25, which, yes, 5 does go into each of these. So we can say 17 over 5, and that's going to be in kilometers per hour. So again, just be aware of signs, make sure you copy things down, and be very careful. I hope that helps.